Hi everyone. Today's session is about the hybrid store design pattern, which Venice supports, but not only Venice, other systems support it too. I wrote a blog post about it a few months ago. I suggest we just go over it. It's like about the equivalent of a one-pager, so pretty short, and I think most people here are already familiar with what it is anyway, so that part is probably not going to take too long. And then I was thinking we can just like think about what are the implications of that pattern, what are like maybe other design patterns that can be built on top of this one. I don't have any prepared material for this second part, so I'm thinking it can be just a free-flowing conversation. So does that sound okay?
Yes.
I'll share my screen about this short post on the hybrid store design pattern, which I don't think should take very long to go through. You can see what I'm sharing now, right?
Yes.
Yes.
Okay. So one way to think about the hybrid store design pattern at a very simplistic, like bash level or shell level would be that you have a directory. In that directory, you have subdirectories such as, V7, V8, essentially they're versions of the data set. And then also at the root of that directory, you have a symlink, which is the current version, and it points to one of those directories, right? So that's like the simplest way to kind of set the context. Of course, in Venice, these are not directories on the file system. There's a whole stack serving this purpose and using RocksDB and whatnot. But it's just to explain the idea, right? So technically, you could implement the hybrid store design pattern like just on your file system if you wanted to. Now, the idea of the hybrid store design pattern is that it is a recipe for handling batch data sources and real-time, or we could say streaming data sources, right? So these have different characteristics, of course. The batch data source is one that refreshes the entire data set periodically, let's say once a day or once an hour or whatever interval, maybe even once a week. And then the real-time data source is one that continuously produces write operations. And so how do you merge those two together, right? There are other takes on how to do that that came before in the industry. There's the Lambda architecture, there's the Kappa architecture, and the hybrid store came after those. And I think it's kind of a natural evolution within that same space is the way I think about it. So the way that this recipe or this design pattern works is there are essentially 4 steps that are fairly easy to walk through, and that's what we'll do now. The first step is like the initial steady state. In that state, the system, here we're presenting that it has only a single dataset version. I'm calling it version N. And there is the current version pointer there that points to that. There's nothing else to point to in that case. So any requests to read data from this resource will go and read the data from version N, because that's where the current version pointer is going to. And then the writes are coming in continuously from the real-time data source, which the real-time data source is putting those writes into a real-time buffer topic, right? Or you can think of it as a queue. We just call it the real-time buffer. And then the writes are continuously ingested into dataset version N. So that's the steady state. Writes are coming in asynchronously via this buffer, and reads go to the one and only version. So that's like not that interesting so far, right? This is just to set the context. But then in step 2, we get the batch data source that wakes up and becomes part of the action. So when a batch job runs and produces a new version of the data set, we can say that this is the future version, right? Or version n+1. So what's going to happen then is that the system which implements the hybrid store design pattern will dynamically instantiate resources to hold this new dataset version. And those resources are independent across versions, right? So there are some resources dedicated to version N and some separate resources dedicated to version N+1. And importantly, at this point, all the system is doing is just bulk loading the output of that batch job into the future version, while in terms of reading data, everything is still going through the current version pointer to the same dataset version as before, which is version N. Then at some point, the bulk load finishes. And that's kind of the interesting part here of the hybrid store design pattern, step 3, where after the bulk load finishes, we get into the real-time buffer replay phase. And that's where it starts making sense. Why is there a real-time buffer in the first place, right? So the buffer replay looks back at some point in time in the past within the buffer, like it could be 24 hours ago or whatever. It's configurable. So the user can decide how far back they need to go within the buffer following this batch push. And so it starts consuming past data, past but recent data from the real-time buffer, and applies it into the future version. And meanwhile, data also continues to be applied from the tail of the buffer into the current version. So both of these versions are consuming the real-time buffer, but they're not progressing at the same rate, right? The version N is consuming the most recent events independently, and version N+1 is catching up as fast as it can from wherever it started up to now. And at some point, the buffer replay phase finishes as well. And that leads us to step 4, which is the final steady state. And that is when finally the current version pointer switches over from version N to N+1. And at that point, version N, which previously was the current version, now becomes the backup version. And version N+1, which previously was the future version, now becomes the current version, right? And then we can keep both of these versions updated continuously, meaning that if for any reason the user detects that the new version of the dataset has any kind of degradation, maybe they detect like business metrics are dropping, or however they detect that, then they can trigger a rollback to the last backup. So it's important that the backup continues being refreshed as well. And at some point, according to configured backup retention policies, we can get rid of the backup if it's too old or whatever. These are all just kind of surrounding details. They're not necessarily part of the hybrid store design pattern itself. I'm just kind of going out of scope a little bit in terms of how what else we do in Venice around that. So that's the hybrid store design pattern in the abstract. As Venice developers, you probably know that we are providing this. And I think there are some Venice specific details of how we do that that kind of go beyond the general design pattern, but which can be interesting also. So we could discuss those. But before we kind of move on to the Venice specific details, is there anything anybody wants to say to comment on this or ask any questions on this? It's fine if not.
Maybe I'll just ask one question, I guess. So all companies have this design pattern, right? Like the hybrid design pattern. And as far as we know, is Venice the only open source?
Yeah, as far as I know, Venice is the only open source implementation of this. There might be others that I'm not aware of in terms of open source. We are definitely aware of several proprietary implementations of this pattern. So at LinkedIn, we have 2 more systems doing this. We have the search infrastructure and the graph serving infrastructure. They all basically follow that pattern. The specific implementation details of how they built it are a bit different from the Venice specific details, but everything I presented here in the abstract is the same basically.
Recently, we had this one folks in our open source channel, the KV Pinterest folks.
Yeah.
They
Yeah,
built a
exactly.
store that was very similar to ours, and use case also very similar.
Yeah, that's right. So Pinterest did a talk at Scale, which is available online if you want to catch it. And around the 6-minute mark, if I recall correctly, they discussed this. They mention it just in passing, but basically they have the same pattern implemented in that system as well. So yeah, it's a common pattern, I think, at this point.
I have a question. So if we have the design button here is for our Venice is a derived platform. Is that possible? I don't know. I'm just thinking out loud. Like, is that possible for this pattern to apply into a sort of truth database, or would it face any challenges on that?
Okay. Yeah, that's a good question. In terms of applying this pattern to source of truth data, I think it's a little bit challenging. Theoretically, anything is possible, right? But I guess it's a weird use case, I think, for source of truth data, in the sense that source of truth data usually is slow changing, let's say. Even if it's fast changing, it's usually only incrementally changing, right? I haven't really seen a use case where the source of truth data needs to be swapped entirely, because if it does need to be swapped in its entirety, then that kind of hints at the fact that the batch of new data that is going to get swapped in comes from somewhere, right? And if it comes from somewhere else, then it's probably a derived data use case. But yeah, so I mean, never say never. Like maybe there exists a use case where it would be source of truth and it could use this kind of pattern. But it doesn't seem to be a very good fit, in my opinion, for source of truth use cases.
I think the other one is source of truth use cases are generally strongly consistent, like they, but the versioning concept inherently make it eventually consistent.
Yes. But I'm just thinking about like because we call it the design pattern
Yeah.
for the store. Feels like we like any database should somehow think about this design pattern. So I was thinking like is that like leverageable in different style of setup or I mean because it's already
Well,
hybrid, so it's kind of unique already. But yeah, I
well,
think
here
gradually
is
yeah, go ahead.
here's something where like because it got me thinking when you said like every database should have this. Well, uh, maybe in the sense that think of a typical source of truth use case, which would be, let's say, you have a table in MySQL, right? And that's like a source of truth table. You have writes going into it, one row at a time, or maybe small batches of row at a time. But then the DBA wants to create a new secondary index on that table, right? How should that happen? Well, if you're using Postgres, there's something somewhat sane happening where it kind of builds the index in the background in a way that is as non-disruptive as possible. If you use MySQL, then there's probably a slightly more insane thing happening where like kind of locks up everything for a while and like rewrites everything, and it's like kind of a stop the world pause. But maybe the hybrid store design pattern should be essentially what the database uses to build the secondary index, right? And so that could allow a source of truth database to non-disruptively in the background generate that secondary index data structure, and then at the very end, when it's like when the sort of real-time buffer replay is caught up, then at that point maybe it has a very small like locking duration where it doesn't accept any more writes, finishes catching up, and then after that the secondary index becomes transactional to the main table, right? So maybe like that could be some sort of way that you apply this in a primary data setting, but even there, like you could say the main table is the source of truth and the secondary index is derived data, right? Even though it's the same data, but it's like the index is derived data. So I guess it's a matter of definitions maybe, but yeah, anyway.
I feel like the derived data platform is common because today the nearline processing just is very common. So eventually they will write some data to some storage. I think the main difference is about this version management or version coordination or orchestration. They typically handle this version orchestration inside some application instead of building into the platform. That is my observation.
You mean they instead of tie the version to application, we now type the version of data?
Yeah, for example, let's say I have some nearline job pipeline. I write do a database called ABC, and I want to reprocess our data. I'm very likely I will create a new database called CDE, and I manage the version for by myself.
I see.
But you can see, those data are still derived data. They are not a source of true data. I guess Venice, we kind of build this version orchestration into the platform so that users don't need to worry about this version management.
I have one small question about
Go ahead.
the real-time buffer. I want to see like how did we come up with that real-time buffer? Because seems like that one is the entrance of the version diverse, like create a new version and things like that. Like, is that natural to have that one, or like, do we have any other options at that point that we decided to go with the real-time buffer? Or that's the only thing that we feel that is really straightforward? I'm just question because from my fresh, I feel from my point of view, it's kind of new to have that step.
Yeah. Yeah, I think this is a good part to drill into. So let's talk about it. Good question. So the real-time buffer is actually if you look at the whole thing, right? The whole diagram, you can think of it as like let's say the real-time data source is like the database client, right? And then everything else is like the database server, right? And the real-time buffer in that analogy that I'm making is like in what in databases we would call the write-ahead log, the WAL. So why do databases have write-ahead logs usually? They have write-ahead logs because it's very cheap to write sequentially, and we want to have durability, right? So that is the purpose of the write-ahead log. And then, besides writing to the write-ahead log, the database will do some other things, like usually it will at the very least update some data structure which serves the purpose of a primary key index, right? Which could be implemented as a B tree where it's going to change in place some nodes in the B tree, or it could be like an LSM tree, which is what we use in Venice in the form of RocksDB. And in the LSM tree, that part besides the write ahead log, that other part that happens in the write path is updating the mem table, which is an in-memory structure. The commonality between these two patterns, the B tree and the LSM tree, is that, well, in the case of the LSM tree, updating the mem table is volatile, right? It's only in memory, so you don't want to lose that. So that's why you need the durability that the WAL provides. WAL meaning write ahead log. And in the case of the B tree architecture, well, the thing is, in the B tree, you often need to modify in place like several nodes of the B tree. And you kind of have to do that atomically. And so if you crash in the middle, like you updated one of the nodes but not another, then you may end up with like a broken tree, like essentially like dangling references or whatever, right? So in both cases, no matter if you're using an LSM tree or a B tree, you rely on the write ahead log for resilience, because if you crash after the data in the primary key index has been fully and properly persisted, then you can use the write ahead log to replay the in-flight operations and make sure that your indexing structure is healthy, right? So that is the motivation in typical database systems for having a write ahead log. Now, in Venice, I think our motivation is roughly the same as that, but it's also a slight variation of the write ahead log pattern. The differences between Venice and a traditional database are the following. First of all, we have a decomposed architecture. So our write ahead log is Kafka, right? Or any pub subsystem, you could say. And so it doesn't run on the same box as the primary key index, basically, right? So we have Kafka serving as the write ahead log, and then we have Venice servers hosting RocksDB instances, and those are the primary key index. So in our case, we we have those as separate distributed systems. But the real-time buffer still plays the role of giving us durability. Durability even before the primary key indices, or even other indices for that matter, like if we have views or whatever, and we have multiple versions of the data set. Essentially, there are multiple indexes that need to be updated according to the write, and we don't want to block like the write until every single thing got done, right? So we want the write to be as cheap as possible and yet still be durable. So that part is similar. But the difference is that in Venice we don't wait for all of the other indices to be updated before acknowledging to the client that we're done, right? In our case, everything else happens asynchronously. We only acknowledge to the client when the durability has been attained, but not when the readability has been attained, right? And that's a design choice that we made. But yeah, so that's sort of where the real-time buffer fits in. You can think of it as a write-ahead log, but it's also a little bit of a twist compared to the way write-ahead logs are usually used, if that makes sense.
Yes. Makes sense. I don't have other follow-up question for now. Yeah.
Cool. So another thing that we might want to talk about here, which kind of dovetails on the last thing, which is the real-time buffer in Venice is like our write-ahead log, but we don't have just a single write-ahead log, actually. Right? We have one write-ahead log per region, per data center. And maybe I can bring up some other stuff because slides from the last conference are relevant. You see this?
Yes.
So first of all, this is what I was just talking about. The Venice is kind of like a decomposed or deconstructed database, right? The real-time buffer serves as a write-ahead log. The server is the index, and then we even have another topic that we didn't talk about yet, which is the version topic, and that acts essentially as a commit log, right? Which can be used for change capture or for feeding follower replicas and so on. But here in this diagram, we have still just one write-ahead log. What I wanted to say is that in Venice, actually, there are more than one write-ahead log. Let's see. Do you still see this? Oh, it lost the slide I was on.
It's on again, but it's not on the slide.
Yeah. Okay. So that's the one I wanted to show. So here we have kind of the single region view or single data center view of Venice. A write comes into the real-time buffer. It gets handled by the server, the Venice server, which the one which is acting in leader replica mode. And then that server writes to a second topic, which is the version topic. And then that version topic is consumed by a variety of things, including additional replicas. which are follower replicas. In the multi-region setup, there are multiple real-time buffers. There's one real-time buffer per region. And so that is also kind of a twist on the typical write-ahead log pattern, in the sense that you can call it maybe like a multi-WAL pattern, multi-write-ahead log pattern, in a sense. What this gives us is that writers can quickly get durability from the local data center without needing to wait for all data centers to have processed the right operation. And then by carefully designing and constraining the types of write operations that are supported, we can also provide the guarantee that that there will be guaranteed eventual consistency, right? And that is achieved with conflict-free replicated data types, right? So we can deterministically, or you could say idempotently, apply the writes, even though they come from multiple buffers and there is a race condition between the buffers, right? So the buffers are not globally ordered in any way. In fact, those buffers can become fully unavailable for extended periods of time, and then when they do become available again, we could catch up on past write operations. So there is no timing component at all. It will deterministically handle late arriving write operations. So that is kind of a property of that architecture. And then what it looks like if you present like two full regions here, there's like the red region and the green region here. Both of them have their own buffer. Both of them have their own servers and their own commit log, the version topic. And the leader replica in each of the region guarantees the eventual consistency via deterministic conflict resolution, right? So that's kind of the idea. And yeah, and so this is sort of a maybe tangentially related to the hybrid store design pattern. But it's basically the same components that are part of the hybrid store design, which also help here handle the active-active replication in a eventually consistent way.
I have a question.
Mhm.
I see in the method of the real-time buffer we have delete.
Mhm.
Maybe can you explain a bit on like why we delete? Because my naive thought on this is we want it to be there to be able to replay. That in which case we want to clean it up or like delete, or like what exactly are we deleting here?
Yeah. So in Venice, when we delete, in Venice, the data set is made up of, you could say, key value pairs, right? Or you can think of them as rows, but there are some columns of the row that are part of the primary key, right? So when a delete comes in, what happens is that we do delete the data. That part is gone. We don't like soft delete the data, in the sense that we don't keep the data but just have a flag saying, you know, don't show this. The data is actually deleted, but the value part of the data is deleted, but the key is retained. A row that used to be present but then got deleted will become kind of an empty row, you could say, where only the key columns are populated. And then the value columns, you could say, are truly deleted. And then that and we do retain also a timestamp of when the deletion happens, right? So that essentially is a tombstone. And then that tombstone is used as part of the deterministic conflict resolution, so that if a late arriving write operation is consumed, then and it attempts to write to a deleted row, then we can compare the timestamp of the late arriving operation against the timestamp of the tombstone, and we can decide, even though at the physical level that write operation arrived after the delete, maybe at a logical level it actually is more recent, right? And if it is more recent, then that row will reappear, so to speak, but it will reappear containing only the data present in that latest write operation. Any of the data prior to the delete is still gone, right? So that's why I'm saying it's a true delete. It's not a soft delete. So that is kind of the design of how the deletes are handled, if that makes sense.
How about the update? Like in what case the real-time buffer has update, but the version topic not having any update method?
Wow, you ask all the right questions. We didn't coordinate at all, but this is like exactly the stuff I was hoping to discuss. So that's great. Keep them coming. Yeah, the way the updates work is that the update can apply to any of the columns of the table, or in a document model kind of sense, we could say any of the top level field of the document, right? So the document is allowed to have nested structures in it, but as far as the update functionality is concerned, we can only touch the top level fields. So any subset of those top level fields can be mutated. And that means, let's say for a scalar column type, like a string or a number or a Boolean, that kind of stuff, then we can just set the value of that field to whatever the write operation wants to set it. And then for collection types, like maps or sets, for those, we can either mutate the whole collection, or we can mutate individual elements of the collection, right? So this is the collection merging part of the update API. So for example, if the field is a map type, then you can say, I want to add this key value pair in that top level map, or I want to remove that key from that top level map. So the important thing to remember with the update API that we offer is that the writer need not know anything else that's present in the document or in the row. It only needs to declare what are the changes that it wants to do. And then the leader replica takes care of merging the incoming write operation into whatever was already there. And that is, again, done as part of the deterministic conflict resolution logic. And as part of that, we look at timestamps, like I hinted at earlier in the delete and tombstone example. And so the outcome is that for a given update operation, which is associated to a single, update timestamp, right? The fields that are mutated in the update operation are either gonna lose the conflict resolution, meaning that they're going to be fully ignored, or they're going to all win the conflict resolution if all the fields have a if the update operation has a higher timestamp than the timestamps of all of the previously written fields. So this is the completely lose or completely win scenario. And there is even a partial win scenario that exists, which is that if the existing record had different timestamps for each of the fields, it is possible that the incoming write operation wins on some of the fields and loses on other fields. And so it could be partially applied. So these are all valid outcomes. And because we have all of these possible outcomes, we can guarantee the eventual consistency again. Then at the end of all that, the leader replica will take the end result and will write it into the version topic. So that's an important step. But the version topic, which we can also call the commit log, like I said earlier, importantly, that one always contains the fully materialized row or full document, if you wish. So even though the real-time buffer, also known as write-ahead log, can contain an update operation which touches only a subset of fields, the event in the commit log or version topic is going to always contain the full row. And that makes it easier to implement the follower replicas as well as the change capture client and all that stuff, because those are interested in the full row, not just the subset of updated rows. So that's the overall way it works.
Yes.
Cool.
I probably have a question. It's actually very inspiring to think about the buffer, the real-time buffer as a write-ahead log. I never thought that way. But in the database systems, there's another concept, the transaction, ACID transaction, which is like very related to the write-ahead log, right? And it seems like we have all the ingredients to implement that. Have we ever been asked in the past to implement any transaction concept or something like in our system?
Yeah, that's a very good question. So currently Venice does not promise any ACID properties. Should it or can it are good questions to ask. So I guess I think anything is possible. So if we were determined to do that, I think we could. Like for example, like one way that you could do it is you could say, well, the producer client which writes into the real-time buffer will not only write to the real-time buffer, but it also will, connect to the servers and then send some kind of operation, some kind of long poll operation to the server and ask it, let me know when you fully processed that, message ID that I just sent into the write-ahead log. And if you waited on that, then the producer client would not be just a producer anymore. It would be more like a regular key value store client that has strong consistency, right? In the sense that you could make it so that it returns not only when the data is durable, but also when it is readable. So this is like implementable. I don't necessarily think that would be like a very good implementation of a strong consistency key value store, because if strong consistency is a requirement, then it probably makes a lot of sense to have the write-ahead log on the same box that you have your index. It's just going to be like more like faster and more efficient to do it this way than in the decomposed way that we do it. So anyway, like can be done, but I don't know if it's actually, competitive in a sense compared to traditional databases, if we were to do it. Another thing I would say is, now circling back to the hybrid store design pattern, possibly it's a good thing actually to not offer strong consistency. I think a case can be made for that. So I got like basically the same diagrams I was showing earlier. I was writing that blog post that I showed in the beginning while preparing the slides for this conference. So it's basically the same content. So here in the hybrid store design pattern, importantly, when we get to the real-time buffer replay phase, I think it actually makes a lot of sense to constrain the supported operations to asynchronous ones only, right? In the sense that if the real-time data source must model all of its write operations as asynchronous and is explicitly not given the guarantee of strong consistency, then it can avoid pitfalls where it would rely on the strong consistency to decide what the content of the write operation is, but then that decision making could not readily be applied as part of the buffer replay, right? Whereas if the operations are only asynchronous, then in the buffer replay phase, there's no problem, right? It can be asynchronously applied to version N today, and then asynchronously applied to the future version even tomorrow, and there's no problem at all, right? So in that sense, I think it's a positive constraint, if that makes sense.
Probably I'm not mean it's a strong consistency sort of transaction. Maybe it's an eventual consistency transaction. For example, like you can group a set of operations, then send to the Venice. Then the sort of the requirement is to either apply the the whole set of the operations or none of them. And probably recover. We should be able to recover from the middle. It's something just a random thought, nothing serious.
Yeah, I mean, it's good to consider, like, how should the system be extended? Well, how can it be extended, and whether it should be extended that way, and what are the implications, right? Like, possibly, like another way to look at it is, well, maybe Venice should have a strong consistency mode, but when you're in the strong consistency mode, maybe batch pushes should be disabled, right? Maybe those should be mutually exclusive functionalities, because maybe it doesn't really make sense to combine them. But the same system could support both kind of workloads, right? So there's a lot of ways to organize this.
Another thing is, for example, if we already have such offering, for example, Lincoln already leveraging TiDB to achieve this goal. Whether we should integrate, or build a duplicate layer inside our Venice. I mean, from the ROI point of view, it is hard to justify.
Yeah, and TiDB or some other system that's been designed from the ground up to be a strong consistency system is almost certainly going to perform better than trying to retrofit consistency on top of Venice, right? But so, yeah, I mean, those are always nuanced conversations. Like, can something be done? Usually the answer is yes. Should it be done? Sometimes that's a different answer, right?
Thanks.
Yeah, I have a question. So I assume you have a present this hybrid store pattern in multiple forum, the public forum already in the past. So have you received any very concrete feedback regarding whether this pattern is being used by some other company as well, or it can benefit, other company too? Um,
So I would say like here and there, some people have mentioned that kind of various things. Like at one time I was presenting this at a meetup, and I think somebody said like, oh yeah, like it's pretty tedious needing to manage this like replay of real-time writes after a batch push, and like it sounds like they were doing something manually, and that it was an interesting idea to have the system kind of support it out of the box in a first class way. In other cases, I think, you know, as in the Pinterest case, we've heard that they did build that as a, first class supported thing at the infrastructure level so that, well, exactly so that users don't need to deal with that, which, can be a little troublesome. Um, um, but I think like there are also a lot of people that haven't really heard of it yet. Or at the very least, they haven't heard of it under that name. Like I think it's basically it doesn't really have a name yet out there. So in Venice we call it hybrid store. And that's why basically I called it hybrid store design pattern, right? Just kind of copied the name from the Venice design, which I think is a, an okay name for what it is. But I think it's important as an industry that we have a name to designate it. That I'm hoping that by calling it that and by extracting the generalities, like not getting stuck in the Venice specific details of it, but looking across, like we know of at least 4 different systems, including Venice, that do that. Like what are the common points, and extracting those as an abstract design pattern, I think, I hope at least, should be useful in terms of helping that conversation going forward.
Can I ask? Sorry.
Yeah, go ahead.
So I want to ask about because we have the real-time buffer over there. Do we have any SLA for the version to change the version n to n+1? Because I assume the real-time buffer would cause some delay to replace. But do we have any SLA to saying like by this latency the version n+1 should be up, or we don't have that?
Well, I guess like by default, the push job times out after 24 hours, and the push job includes like steps 2 and 3, right? It includes the bulk load phase and the buffer replay phase. That push job timeout is configurable, so some users can decide to extend it further. That's not too common. In some cases, they decide to make it a tighter timeout, and that's a bit more common. Um, but again, it includes like both of these phases, the bulk load and the buffer replay. We don't really have any SLA on like just the buffer replay, how long it takes. I think that was your question, if I understood correctly.
I think it comes from the question that is that matter which version we are serving from customer point of view. Like for example, customer 1 version n+1 instead of version n. is there a way to fast forward it? I think we have like forward, roll forward thing, but I don't know from customer use case point of view, is that really matters on which data set version they are querying from? And if that version matters, then from customer point of view, I would hope to see some promise there. That's why I asked on that, because I see the real-time
Okay.
buffer gonna have some delay. Yeah.
Well, so I don't know if this is where you're going, but I will say the expectation for using this capability is that the versions are compatible together, right? So the version N+1 should be a more fresh version of than N, but it should be conceptually the same, right? Like, for example, the common case is that the batch job is like a ML training job, and it will retrain the same model on fresher inputs. But it's the same model, right? So that means on the reading side, the application is using some corresponding model for inference, and they would want that inference model to be fed, ML feature data coming from the freshest available version of the data, but always like tied to that same model, right? So there is an anti-pattern that we see sometimes where people use this mechanism to push data generated by a whole new model, and that can get pretty dicey, right? If going from version N to N+1 is a different ML model and it's like not compatible with the old one, then in that case, the application reading would need to like be in lockstep with the dataset version swap in Venice, and would need to like switch what inference model it's using, and so that gets pretty complicated, and is like not recommended, right? So in the cases where they need precise control of which batch push data to query, then typically I think we would push those users towards setting up separate stores, right? Or else they can also set up within the same store, have some keys that are generated by one model and some other keys generated by another model, and they all exist within, essentially all the models exist in all the dataset versions, right? So they're all available there. The application can choose to query one key or another. So yeah, so I would say that hopefully that makes sense.
Yes.
I do need to drop off now personally, but if you guys want to keep going, definitely feel free, keep it going. But as far as I'm concerned, I'll need to drop off, unfortunately. But I think it was a great session. Thanks, everyone.
Thanks, Philip.
Thank you.
Thank you.